everyone, welcome back. In this video, we'll introduce the second of our discrete distributions, which is the geometric distribution. We'll start by defining the geometric distribution and talking about some properties of the geometric. Next, we'll look at how to find geometric probabilities, both by hand and using R. And then finally, we'll talk a little bit about the expected value and variance of the geometric. So let's jump into the geometric distribution itself. We say that a random variable y has a geometric distribution with parameter p if the probability that y takes on some value little y is equal to 1 minus p raised to the y minus 1 times p. Essentially, what we're looking at with the geometric distribution is a way to model how many failures we're going to observe before we hit that first success, that first time we observe the outcome we care about. Now, depending on that predetermined probability of success, p, this geometric distribution may look very different. For example, take a look at the graph on the bottom right. This geometric distribution has a very high probability of success, p equal to 0.9. So it's very likely that we'll observe that first success on the first trial, maybe even the second. Once we hit about 3 trials, this is 2, here's 3, the probability that we'll need to go that far before observing a success becomes negligible. Contrast that to lower probabilities of success, say probability of success 0.5, 0.1, or even 0.001, the smaller that probability of success becomes, the more random trials we need before we observe that first success. So let's take a look at an example. We have a baseball player whose batting average is 0.3 or 300. When the player comes up to bat, this means that there's about a 30% chance that this player will get a hit, about a 70% chance that something else will occur, a strike, for example. Find the probability that after 3 times at bat, for those of you unfamiliar with baseball, after 3 strikes or 3 misses, you're out. We want to know the probability that the player still hasn't gotten a hit. So we'll let y be the number of hits until the player gets a hit, so is successful. Y then follows a geometric distribution, assuming that each time at bat is independent, with probability of success 0.3. We want to find the probability that y is greater than 3. So even after the 3rd trial, the player has not gotten a hit. We can find that by taking 1 minus the probability that they get a hit on their first try, plus the probability of a second, plus the probability of being successful on the 3rd. So we get, plugging into the geometric formula, 1 minus 0.3 for the probability that they're successful the first time, plus 1 minus 0.3 times 0.3 for the probability they're successful the second time, plus 1 minus 0.3 squared times 0.3 for the probability they're successful the 3rd time. So then we get, when we plug all this in, do all the calculations, about a 34% chance that even after the 3rd at bat, the player has not gotten a hit. Now we can find these probabilities in R using the geom family of functions. So just like binomial, we have a suffix indicating the distribution, in this case geom for geometric, and then the prefix indicating the type of calculation we'd like R to do. However, R defines this distribution a little bit differently. And let's see if we can maybe back solve for how R is thinking about the geometric distribution. So we know from our definition that the probability that y is equal to 1, or the probability of a success on the first at bat, should be 0.3. However, if I use this d suffix, which should calculate probabilities, plug in 1, probability of success 0.3, I get a slightly different answer, 0.21. Okay, so let's take a look at this cumulative probability, the probability up to a point. We know, for example, from the previous problem that given this geometric distribution, the probability that y is less than or equal to 3 should be 0.657. However, we get something a little bit different, again, when we do this calculation. We get 0.7599. So why the discrepancy? Well, it turns out that R is actually defining this distribution in terms of the number of failures before the first success. So R is looking at this input here in the first argument and saying, okay, well, that's how many times you'll fail before you get the first success. So on the previous slide here, when we plugged in 1, what this was actually calculating was the probability that the first success will occur on the second trial. So for us, in order to work with this distribution in the way that we have defined it, or the way that we have parameterized it, we will just simply subtract 1. So for us, in order to get the probability that y is equal to 1 to be 0.3, we'll use the dGOM function. We'll just take 1 minus 1 as opposed to 1. And here we get the probabilities that we were expecting. So just remember, there is a slightly different definition or a slightly different parameterization in R versus what we're working with in our textbook. Okay, so let's talk about some properties of the geometric distribution. The expected value of y, so the expected number of trials in order to reach that first success, is 1 over the probability of success, so 1 over p. The variance is then 1 minus p divided by p squared. So for our baseball player, let's find the expected value and variance of the number of times at bat before they get a hit. Now remember, we're assuming that the probability of success p is 0.3. So our expected value will then be 1 over 0.3, or 3.33 repeating. The variance here will be 1 minus p divided by p squared. So 1 minus 0.3 over 0.3 squared, get a variance of about 7.78. Now, how do we know whether or not a situation is a binomial distribution or a geometric distribution? There are some key differences between these two. First, let's look at the binomial distribution. The binomial distribution has a fixed number of trials, n, so we know that we're going to attempt the experiment n times. The probability of success on each of those trials is fixed, we'll call that p, and we're assuming that the trials are independent. So in the binomial distribution, what we're really looking for is the number of successes in a fixed number of trials. Now contrast that with the geometric distribution. When we're using a geometric distribution to model a scenario, we're going to keep going. We're not going to stop until that first success is reached. So rather than having a fixed number of trials, we have a fixed number of successes that we'd like to reach, specifically the first one. The probability of success is fixed here, so that's constant, just like with the binomial distribution, and the trials are independent, again, just like the binomial distribution. So there are some similarities between these two. In the next video, we'll introduce some more discrete distributions. I'll see you then.